we're going to go on a little journey from the absolute tiniest piece of silicon all the way up to the vast abstract idea of the cloud. We're going to pull back the curtain on the hidden tech that makes our entire digital lives tick. It's a pretty incredible story, so let's just dive right in.
I mean, it seems so simple, doesn't it? You just tap a screen and poof, a video starts playing. But behind that one single action is this incredible high-speed ballet of hardware and software. We're talking about signals traveling across custom-built chips, zipping through global networks, all orchestrated by a kind of digital brain. In this explainer, we're going to follow that signal and see exactly how it all works.
You know, everything really starts with a chip. It's the silicon heart of all modern technology. But here's the thing, not all chips are created equal. Engineers have to make this fundamental choice between two very different approaches, each with its own serious pros and cons. It's really a tale of two chips, the ASIC and the FPGA. Okay, so first up, the ASIC. The best way to think about an ASIC is to picture a custom-built Formula One race car. Every single component, every curve, is engineered for one thing and one thing only, to go around a track faster than anything else. You can't take it to the grocery store, it's not versatile at all, but for its one specific job, absolutely nothing is faster or more efficient. That's an ASIC. Now, if the ASIC is our Formula One car, then the FPGA is like a super high-performance Lego Technic set. It's this collection of powerful generic building blocks that you can put together and then take apart and reassemble into almost anything you can imagine. A race car one day, a heavy-duty truck the next. Yeah, it might not be as perfectly tuned as the custom-built car, but its incredible flexibility means you can adapt it to new challenges without having to start completely from scratch. So, this table really gets to the heart of it all. As you can see, the ASIC, our Formula One car, is the clear winner when it comes to raw performance and power efficiency. No question. But take a look at the development cost and the time to market. FPGAs are way cheaper and faster to get up and running. We're talking months instead of years. So the big question for engineers is always, what do you value more? Raw, unadulterated power, or the ability to adapt and get your product out the door quickly?
And this chart, wow, it just spells it out, doesn't it? An ASIC can be 5 to 10 times more power efficient. And look, this isn't just some minor detail. This is a total game changer. For anything that runs on a battery, think about your smartphone, getting you that extra hour of life. Or for these massive data centers where electricity bills are just astronomical, this level of efficiency is absolutely critical.
So when does it actually make financial sense to build that Formula One car? Well, this number gives us a pretty good clue. ASICs have this huge upfront design cost, but each chip you make after that is cheaper. So for a product with a small production run, FPGAs are a no-brainer. But once you're planning to make tens of thousands of units, you hit this crossover point where that big investment in a custom ASIC really starts to pay for itself.
Okay, so a chip, no matter how powerful it is kind of useless in isolation, right? It's like a brain without a nervous system. To do any real work, it has to communicate. And that brings us to the fascinating world of hardware language, how we turn the abstract ones and zeros of the digital world into actual physical signals that can travel through a wire.
Now, to make sense of this super complex world of network communication, engineers came up with a kind of roadmap. It's called the OSI model. It's basically a 7-layer framework that breaks down the whole process into manageable chunks. And we're going to start our journey at the very, very bottom, layer 1, the physical layer. The physical layer has one fundamental job. It takes the abstract language of computers, those ones and zeros, and turns them into something real. It transforms those bits into electrical pulses zipping down a copper cable, or flashes of light in a fiber optic line, or even radio waves flying through the air. It is the true bridge between the digital world and the physical one. So how in the world do we send information on a radio wave? Well, the secret is this really cool trick called signal modulation. Think of it like a smoke signal. A steady stream of smoke is your carrier wave. By changing the smoke puffs, making them bigger or smaller, or sending them faster or slower, you can send a message. That's pretty much what we're doing with radio waves, and it's the basis for everything from your car radio to your Wi-Fi. All right, so now we get how a single signal travels, but let's zoom out a bit. How do you manage a network with thousands, or heck even millions, of these signals all flying around at once? The answer lies in a really clever design principle. You separate the brain from the brawn. So first up, you have the control plane. This is the network's brain. Think of it like air traffic control. The control tower doesn't fly the planes itself, but it has a complete view of the entire airspace. It's making the big picture decisions, which flight paths are open, how to avoid collisions, and where every single plane should go. It's the strategic, thinking part of the system.
And then you've got the data plane. This is the network's muscle, its brawn. So if the control plane is air traffic control, the data plane is the actual fleet of airplanes. Each plane has a very simple, very focused job. Take off, follow the flight path the control tower gave you, and get your cargo to its destination as fast as humanly possible. It is all about execution and high-speed forwarding. This table gives us a fantastic side-by-side. Notice the difference in speed. The control plane can afford to be a bit slower, but the data plane has to be lightning fast. And look at fault tolerance. If the air traffic control tower has a brief power outage, the planes that are already in the air can keep flying for a bit. But if a plane's engine fails mid-flight, that's a catastrophe. The data plane simply cannot go down. So why go through all this trouble? Well, the benefits are huge. You can scale your brain and your brawn independently. A failure in one doesn't automatically take down the other. And you really get the best of both worlds. You get smart, centralized management from the control plane with crazy fast, decentralized execution happening everywhere else in the data plane. This architecture is pretty much the foundation of every modern scalable system out there. Okay, now it is time to connect the dots. We've talked about specialized chips and the split between network brains and brawn. So let's look at how these fundamental ideas come together to build the actual cloud services that we use every single day. Remember our Lego blocks, the FPGAs? Well, this is where they become a legitimate superpower. In a project they call Catapult, Microsoft basically puts FPGAs into their servers all over the world. What that means is they can build custom hardware to speed up Bing searches today, and then tomorrow they can just reconfigure those exact same chips to power a brand new AI model. It's like having a data center made of Lego, and it gives them incredible, game-changing flexibility. Now, if you've ever worked with cloud applications, you have definitely heard of Kubernetes. And it is a perfect, real-world example of our brain and brawn analogy. The control plane parts, like the API server and the scheduler, they're the air traffic controllers, deciding where all the applications should run. And the data plane components on each machine, the kubelet, the container runtime, they are the airplanes, actually executing those instructions and running the code. Now let's get back to our Formula One cars, the ASICs. This is where they absolutely dominate. Inside a massive data center, you are moving just unbelievable amounts of data, and to handle that kind of speed, you need custom-built chips. This diagram, yeah, it looks a little complex, but it's showing us how these specialized ASICs work together to create a super-fast network, directing traffic with mind-boggling precision and speed. And this right here, this is a peek inside a high-performance network switch. And it's a perfect illustration of everything we've just talked about. The PFEs you see there, those are the brawn, packed with our Formula One ASICs. They are all about moving data at incredible speeds. And you can actually see how the data traffic is kept totally separate from the control traffic, the instructions from the brain. It's the brain and brawn model, built right into the silicon. So as we've seen from the chip all the way up to the cloud, every single design decision really comes down to one fundamental tension, a core conflict that every single engineer has to solve. And this quote from the source material just says it all. Do you build something that's perfectly optimized for today's needs, the fastest, most efficient solution you can possibly make? Or do you build something adaptable enough to handle the unknown challenges of tomorrow? This isn't just a technical question. It's a deep strategic one that literally shapes the future of technology. So I'm going to leave you with this final thought. As our digital world just continues to explode and evolve, which path are we going to choose? Are we going to bet on the raw power of specialized hardware, our Formula One cars, or on the endless possibilities of adaptable systems, our Lego blocks? The choice we make is going to shape the future of tech in ways we are only just beginning to imagine. Thanks for joining me on this.